From black holes to the fate of the cosmos, here are the greatest mysteries science still can't explain. Have you ever looked up at the night sky, a velvet canvas sprinkled with diamond dust stars, and felt a profound sense of wonder? A feeling that you are part of something immeasurably vast, ancient, and deeply mysterious? I have. That feeling is the engine of science, the very same curiosity that drove our ancestors to chart the heavens and that propels us today to the farthest reaches of space and time. We've learned so much. We've mapped galaxies, decoded the light of distant stars, and even glimpsed the dawn of time. Yet, for all our discoveries, the universe holds its greatest secrets close. The known is but an island in an infinite ocean of the unknown. We stand on the shore of that island, peering into the cosmic abyss, and the questions that stare back are the most profound we can ask. These aren't just puzzles for scientists in labs. They are questions that touch the very core of our existence. What is the universe made of? Where did it all come from? Where is it all going? And are we alone in this grand cosmic drama? The journey to answer these questions is the greatest adventure of the human intellect. So, come with me. Let's embark on a voyage together, aboard our spaceship of the imagination. We will travel to the edge of understanding, where the familiar laws of physics begin to fray, and the cosmos reveals its most enigmatic face. We'll explore the darkness between the stars, the beginning of time itself, and the very fabric of reality. This is not just a list of unsolved problems. It is an invitation to wonder, to question, and to share in the magnificent, ongoing quest for cosmic truth. The universe is waiting. Our first stop on this journey takes us into the shadows. Look around at the cosmos, at the galaxies spinning in their silent, celestial ballet. You see stars, gas, dust, all the familiar stuff we call matter. But what if I told you that everything you see, everything we have ever detected directly, makes up only a tiny fraction of what's actually out there? About 5%, to be precise. The rest, the overwhelming majority of the universe's mass, is invisible. It's a substance we call dark matter. We can't see it. We can't touch it. It emits no light, no heat, no radiation of any kind. And yet, we know it's there. How can we be so sure of something we can't see? The answer is gravity. We see its influence everywhere we look. We see galaxies spinning so fast that based on the visible matter alone, they should have torn themselves apart, flinging their stars into the intergalactic void billions of years ago. Something is holding them together, an unseen gravitational glue. We see light from distant galaxies being bent and distorted as it passes through space, warped by the gravity of massive invisible clumps of something. This gravitational lensing is like seeing the silhouette of a ghost against the cosmic wallpaper. So, what is this mysterious, invisible substance? That is the trillion-dollar question. For decades, we've been searching. We've built detectors deep underground, shielded from cosmic rays, hoping to catch a fleeting glimpse of a dark matter particle bumping into an atom of normal matter. Is it a WIMP, a weakly interacting massive particle? Is it a sterile neutrino? Or is it something far stranger, something entirely outside our standard model of particle physics? The truth is, we simply don't know. The universe is haunted by a ghost, and we are the detectives trying to uncover its identity. If dark matter is the universe's invisible skeleton, holding it all together, then our next mystery is the force that's actively pushing it all apart. For most of the 20th century, We cosmologists had a simple debate. Will the universe collapse back on itself in a big crunch? Or will it expand forever, slowing down over time? We thought gravity was the only game in town on the largest scales. We were wrong. In 1998, two teams of astronomers studying distant supernovae to measure the universe's expansion rate found something utterly astonishing, something impossible. The expansion of the universe isn't slowing down, it's speeding up. Imagine throwing a ball into the air and watching it. Instead of slowing down and falling back, accelerate faster and faster into the sky, defying gravity itself. That's what our universe is doing. Every galaxy is rushing away from every other galaxy at an ever-increasing speed. There must be a force at work, a kind of cosmic anti-gravity, pushing space itself apart. We've given this mysterious force a name, a placeholder for our ignorance: dark energy. It appears to be a property of space-time itself, a sort of energy of the vacuum that permeates everything. What is this dark energy? The most popular idea is that it's the cosmological constant, an idea Albert Einstein once proposed and later called his biggest blunder. It seems his blunder might just be the most dominant force in the cosmos. But why does this energy have the specific value it does? Our best theories predict a value that is stupendously, wildly larger than what we observe. 120 orders of magnitude larger. This discrepancy is one of the greatest embarrassments in physics. Dark energy makes up nearly 70% of the universe, and we have almost no idea what it is. It's the ultimate cosmic mystery, determining the final, ultimate fate of everything. There are monsters in the universe, not of flesh and blood, but of gravity. Objects so dense, so massive, that their gravitational pull is absolute. Nothing, not even light, the fastest thing in the cosmos, can escape their grasp. We call them black holes. They are the points where the fabric of space-time has been stretched to its breaking point, torn by the weight of a dead star. When a truly massive star, many times the mass of our Sun, runs out of fuel, its own gravity overwhelms it. It collapses catastrophically, crushing itself down into an infinitesimally small point, a singularity. This is the birth of a stellar mass black hole. But there's another, more mysterious kind. At the heart of nearly every large galaxy, including our own Milky Way, there lurks a supermassive black hole, millions or even billions of times the mass of our Sun. Where did these behemoths come from? They are too big to have formed from a single star. Did they grow from smaller black holes, gobbling up stars and gas and merging with each other over cosmic eons? Or did they form from the direct collapse of gigantic clouds of gas in the early universe? We are still piecing together the family tree of these cosmic titans. The true mystery of a black hole, however, lies beyond its event horizon, the point of no return. What happens inside? Our current laws of physics, Einstein's general relativity, tell us that at the centre lies a singularity, a point of infinite density where space and time cease to exist as we know them. But our theories break down there. To truly understand the heart of a black hole, we need a new physics, one that can unite gravity with the strange rules of the quantum world. A black hole is not just an object. It is a cosmic laboratory, a place where the universe is screaming at us that our understanding is incomplete. Every story has an ending. But what about the grandest story of all, the story of the cosmos itself? The ultimate fate of the universe is, honestly, one of the most profound questions we can contemplate. For a long time, the answer depended on a sort of cosmic tug-of-war between the momentum of the Big Bang's expansion and the relentless pull of gravity. If there was enough matter, gravity would eventually win, and the universe would collapse back in on itself in a fiery big crunch, perhaps to be reborn in another Big Bang. A kind of cosmic cycle of death and rebirth. But, the discovery of dark energy really changed everything. This mysterious force is not just resisting gravity, it's overpowering it. With the universe's expansion accelerating, the Big Crunch scenario now seems pretty unlikely. Instead, we face a much colder, lonelier end. The most widely accepted scenario is called the Big Freeze, or the heat death of the universe. As space expands, galaxies will fly so far apart that the sky of a distant future observer will be completely dark, save for the stars in their own local, gravitationally bound group. Over unimaginable timescales, stars will burn out. Black holes will slowly evaporate through a process called Hawking radiation. The universe will grow colder, darker, and emptier, approaching a state of maximum entropy, a final, uniform equilibrium where nothing interesting can ever happen again. Is this bleak vision our inescapable destiny? Or could there be another twist? Perhaps dark energy will grow stronger, leading to a big rip where the fabric of space-time itself is torn asunder. We are living in a special, fleeting moment in cosmic history, able to look out and see the evidence of our origins. Future cosmic inhabitants may not be so lucky. Our universe is vast, perhaps even infinite. But is it the only one? This question, which was once the sole domain of philosophy and science fiction, has now entered the realm of theoretical physics. The idea is called the multiverse. It suggests that our universe is just one bubble in a vast cosmic foam of countless other universes, each potentially with its own unique laws of physics, its own set of fundamental constants, and perhaps even its own dimensions. It's a staggering, really mind-bending concept. Why would physicists even consider such a thing? Well, the motivation comes from several threads of modern cosmology and quantum mechanics. Some interpretations of quantum mechanics suggest that every time a quantum measurement is made, the universe splits into multiple branches, one for each possible outcome. In this many worlds view, there is a universe where you chose a different breakfast this morning, and another where the dinosaurs never went extinct. Another idea, called eternal inflation, suggests that the Big Bang that created our universe was not a one-time event, but that Big Bangs are happening all the time, constantly budding off new universes from a parent multiverse. But is this science? A key tenet of the scientific method is that a hypothesis must be testable. How could we ever test for the existence of universes that are, by their very definition, separate from our own? Some scientists have proposed looking for bruises in the cosmic microwave background radiation, faint patterns that could be the signature of our universe bumping into another in the distant past. So far, the evidence is inconclusive. The multiverse remains a tantalizing, unproven, and perhaps unprovable idea. It's a humbling reminder that reality may be far, far stranger than we can possibly imagine. What is time? It's a question so fundamental, we rarely even think to ask it. For us, it's the unyielding river that carries us from the past, through the present, and into the future. We remember the past, but not the future. We can move freely in the 3 dimensions of space, but we are prisoners of the single dimension of time, dragged inexorably forward. But why? Why does time have a direction, an arrow of time? At the level of fundamental physics, the laws that govern the interactions of particles don't seem to care about the direction of time. A video of two particles colliding would look just as valid if you played it backwards. The most common explanation for the arrow of time lies in the second law of thermodynamics. This law states that in a closed system, entropy, a measure of disorder or randomness, always increases. A pristine egg can be scrambled, but you can't unscramble it. The universe began in a state of very low entropy, a highly ordered state at the Big Bang. Since then, its entropy has been increasing, and it is this inexorable march towards disorder that we perceive as the forward flow of time. We remember the past because it was more ordered than the future. But, this just pushes the question back a step. Why was the universe so highly ordered at the beginning? And is our perception of time just a consequence of this thermodynamic process? Einstein's theory of relativity complicated things even further, showing that time is not absolute. It's relative. It can be stretched and squeezed by gravity and motion. For a photon travelling at the speed of light, time doesn't pass at all. Time, the most familiar aspect of our reality, is perhaps the one we understand the least. It may not be a fundamental aspect of the universe, but an emergent property of a deeper, timeless reality. Look up at the night sky. Our galaxy, the Milky Way, contains, hundreds of billions of stars. And there are actually hundreds of billions of galaxies in the observable universe. In recent years, we've discovered that planets are not the exception, but the rule. It seems nearly every star has a planetary system. With such staggering numbers, it seems almost inevitable that somewhere out there, on some distant world orbiting a faraway sun, life has arisen, and if it has, it's had billions of years to evolve, perhaps into intelligent technological civilizations. So, where is everybody? This simple yet profound question is known as the Fermi paradox. If the galaxy is teeming with life, why haven't we heard from them? Why do we see no evidence of galactic empires, no interstellar communications, no megastructures built around stars? The cosmos is unnervingly quiet. This great silence is one of the most perplexing mysteries we face. Are we truly the first and only intelligent species to arise in our galaxy? Is the leap from simple life to technological intelligence so incredibly rare that we are a statistical miracle? Or are there more sobering possibilities? Perhaps civilizations, once they reach a certain technological level, inevitably destroy themselves. Or maybe the galaxy is a dangerous place, and advanced civilizations practice a cosmic quiet to avoid attracting unwanted attention. Or perhaps they are out there, but we are just too primitive to recognize their signals, like ants crawling on a superhighway, completely unaware of the intelligent traffic whizzing by. We continue to listen, pointing our radio telescopes at the heavens, hoping to one day hear a whisper in the static, a signal that finally answers the question, are we alone? Our cosmic story has a beginning. We can see the evidence for it all around us. We observe that distant galaxies are rushing away from us, which means that in the past, everything must have been closer together. If we rewind the cosmic clock all the way back, about 13.8 billion years, everything in the entire observable universe, all the matter, all the energy, space itself, was compressed into a single point of unimaginable heat and density. This was the moment of the Big Bang. It was not an explosion in space, but an explosion of space. From this primordial fireball, the universe began its long process of expansion and cooling. In the first few minutes, the fundamental forces of nature took their separate forms, and the first atomic nuclei were forged. For 380,000 years, the universe was an opaque, glowing fog of plasma. Then, as it cooled further, electrons and nuclei combined to form the first atoms, primarily hydrogen and helium. At that moment, the universe became transparent, and the light from that era was set free to travel across the cosmos. We can still see that light today, stretched into microwave frequencies by the expansion of space. It's called the cosmic microwave background, the afterglow of creation. But the Big Bang theory, as successful as it is, leaves us with a monumental question. What came before? What, or who, lit the fuse? Our laws of physics break down at the singularity of the Big Bang itself. We have no way of describing that initial moment or what might have preceded it. Was there a before? Did our universe emerge from another, older universe? Or did time itself begin with the Big Bang? This is the ultimate origin story, the boundary of our knowledge, where science meets the profound, awe-inspiring mystery of existence itself. We have journeyed across the cosmos, from the smallest particles to the largest structures, from the beginning of time to its potential end. But perhaps the greatest mystery of all is not out there in the dark, but right here, behind our eyes. It is the mystery of consciousness. Think about it. I am a collection of atoms, forged in the hearts of long-dead stars. You are too. We are, in a very real sense, the universe made aware. Star stuff. Contemplating the stars. How is this possible? How does a collection of non-sentient cells, a 3-pound lump of fatty tissue called the brain, give rise to the subjective, private, inner world of experience? The feeling of warmth from the sun, the beauty of a sunset, the joy of discovery, the sorrow of loss. These are the hallmarks of consciousness. We can map the neural correlates of these experiences. We can see which parts of the brain light up when you feel happy or sad. But that doesn't explain the why. Why does it feel like anything at all to be a collection of firing neurons? This is what philosophers call the hard problem of consciousness. Is consciousness an emergent property of complex information processing, something that would arise in any sufficiently advanced computer? Or is it something more fundamental to the fabric of the universe? Something that our brains have simply evolved to tap into? It is the point where the objective external universe of physics and the subjective internal universe of the mind meet. And we have no idea how to bridge that gap. In our quest to understand the cosmos, we have discovered that the observer, the conscious being asking the questions, is the most profound enigma of all. Our final mystery brings us back to the very foundation of our understanding of reality. For the past century, physics has been dominated by two spectacularly successful, yet fundamentally incompatible, theories. The first is general relativity, Einstein's theory of gravity. It describes the universe on the largest of scales, the dance of planets, stars, and galaxies, as the curvature of a unified fabric of space-time. It is a theory of the smooth, the continuous, the cosmic. It works perfectly for describing the big stuff. The second is quantum mechanics. This is our theory of the very small, the bizarre and wonderful world of atoms and subatomic particles. It describes a universe that is grainy, probabilistic, and full of strange effects, where particles can be in multiple places at once. It is a theory of the discrete, the chaotic, the quantum, and it works perfectly for describing the tiny stuff. The problem is, the universe is one thing. The laws that govern a star must also, ultimately, govern the atoms that make up that star. There must be a single, underlying theory that unites them both. This is the holy grail of modern physics, a theory of everything. A single set of equations that can describe every fundamental force and particle in the cosmos, from the Big Bang to the heart of a black hole. Physicists have been chasing this dream for decades. String theory is one of the leading candidates, proposing that all fundamental particles are just different vibrations of unimaginably tiny one-dimensional strings. But it operates in extra dimensions we can't see, and makes predictions we can't yet test. The quest for unification is the ultimate expression of the scientific faith that the universe is not a random collection of facts, but is ultimately elegant, simple, and understandable. We've travelled to the edge of space and time, and we've returned with more questions than answers. We've peered into the darkness and found that it's not empty, but full of mysterious matter and energy. We've looked at the beginning and the end, and found both shrouded in cosmic uncertainty. From the nature of time itself to the nature of our own consciousness, we are surrounded by profound mysteries. And isn't that wonderful? It means the greatest discoveries are still ahead of us. The grandest chapters of the human adventure are yet to be written. The universe is under no obligation to make sense to us. Yet it does, in so many ways. The fact that we, a species on one small planet, can even begin to ask these questions and piece together the cosmic story is the most remarkable thing of all. The quest for knowledge is a fundamental part of who we are. It connects us to each other, to our ancestors who first looked up in wonder, and to our descendants who will, I hope, solve some of the mysteries we've talked about today and uncover new ones we can't even yet imagine. So, keep looking up, keep asking questions, never lose that childlike sense of wonder when you contemplate the vast, beautiful, and deeply mysterious cosmos that is our home. The journey of discovery is a shared one, and it has no end. There will always be a new horizon, a new mystery waiting just beyond the edge of our knowledge. And the desire to understand is the most noble and human impulse we have. Thank you for joining me on this voyage through the great unanswered questions of the universe.